My name is Thomas Settlemyre. I'm a third-year graduate student at the Cyclotron Institute at Texas A&M University, and today I'll be discussing some theoretical work that we've done regarding dynamical production of E plus E minus in subbarrier reactions of light ions. For some motivation, let's look at some results from a group in Germany at GSI in the 1980s. They found these anomalous peaks in the positron energy spectra for some heavy ion collisions that were not well explained by current theory. Later, a group at Argonne reproduced the experiment and found no evidence of the peaks. To our knowledge, there's no consensus that explains all of these data. We will see if we can explain what's going on with our model. Recently, a group in Hungary populated an excited state of beryllium-8 and observed the E plus E minus created from the transition to the ground state. They found a peak that they believe is explained by a new particle of mass 17 MeV. But there's yet no consensus from the high energy community as to whether this particle exists. So we would also like to take a look at this system of light ions with our model and see if we can explain this peak without the hypothesis of a new particle. Before we look at creation of actual pairs, we'll look at the perturbative effect from virtual pairs, namely vacuum polarization, the process shown in this Feynman diagram. In the 1930s, the correction to the Coulomb energy was shown for small distances, smaller than the Compton wavelength of the electron, to be this log R over R potential. We've studied how including this term can affect the liquid drop model mass formula. And what we found is that it contributes about 1% of a decrease to the total binding energy of the nucleus in general. In subbarrier fusion, two nuclei approach each other, and classically they would stop because they're below the Coulomb barrier and turn around. But there is a finite probability that they would tunnel and then fuse. You can find the probability in the cross-section using an imaginary time technique, and what we've found by including this vacuum polarization correction in particular for the carbon-12 fusion reaction at low energy, we found a decrease of about 15% in the cross-section. We also studied fission, and we found also that there is about a 1% change in the fragment energies when you include the vacuum polarization correction. Our ongoing work is to show the actual production of E plus E minus pairs along this is done by solving the Dirac equation with the background of the Coulomb potential of the two ions. The electron will tunnel through an effective potential and leave behind a hole, which is a positron. We believe that this geometry is the most likely with the E minus in the middle, because it then lowers the Coulomb barrier of the two ions and perhaps can facilitate subbarrier fusion, but this work is ongoing. Thank you for listening to my poster presentation. I in particular would like to thank the Centaur group for the NNSA for my funding. You can reach me at the email address shown here if you have comments or questions, or if you would like to collaborate. Thank you very much.